On to the next example of the brake test. We've got a 2,000 kilogram truck whose brakes can apply 10,000 newtons of force. How much time does it take for the truck to brake from 30 to 10 meters per second? We're looking for time. Maybe you want to go kinematics? Okay. You're given the force, so you can get your acceleration because you also have your mass. Get your acceleration, go to kinematics. Or you can use the impulse momentum theorem. Because we need to relate force to time, we'll call forward positive, making the braking force negative. Final momentum equals impulse plus the initial momentum, and here it is all in one nice equation rather than having to use two. So that's really the big advantage to using our impulse momentum theorem in this instance. We can use square charts we learned about to show the impulse momentum theorem. So here we have an object with a mass of 3 kilograms moving backwards at 5 meters per second, a 4 Newton forward force acting on the object for 6 seconds. How fast does the object go after the force acts? Impulse momentum theorems. Initial momentum plus impulse equals final momentum. Initial momentum plus impulse equals final momentum. Solving for VF gives us 3 meters per second. So the rightward force caused the leftward moving object to stop and reverse direction and go to the right. Here's what the same situation looks like using square diagrams for the impulse momentum theorem. All right, so mass was 3 kilograms, and the initial velocity was -5. So there we go. Plus the momentum, or excuse me, plus the impulse. Starting momentum plus the impulse equals the final momentum. All right, so the impulse force versus time graph. For 6 seconds, there were 4 newtons of force applied. Color that in. And then we can say 1, 2, 3, 1, 2, 3, 4, 5. So this is 15 here, -15. And this is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 24 boxes, positive. 15, -15 plus positive 24 gives us 1, 2, 3, 1, 2, 3, positive 9. 3 meters per second. We know the mass is 3 kilograms. 3 kilograms. It's got to get up to 9. So how do we get there? Up 3. Now suppose instead that the 3 kilogram object initially moving backward at 5 meters per second had a force applied to it that acted this way. For the first 3 seconds, the force increases linear from 0 to 6 newtons. For the last 3 seconds, the force decreases from 6 to 0. Because the force changes, we have to represent the force using a graph of force versus time like this. The impulse would give the area of the force versus time graph, which is 18 newtons times a second. Here's what the same situation would look like using square diagrams. The initial momentum is still the same, -5 meters per second times 3 kilograms. And then we have that impulse, force versus time graph. The force is changing as time goes on for the first 3 seconds, and then the last 3 seconds it changes again. Now our final velocity, again we're going to go 3 kilograms here. Our mass hasn't changed. So it only needs to go up 1. So that's what the final velocity would be. There's your numbers. Sorry if I was a 9. The square diagram for impulse was now just the graph of force versus time. The area of the force versus time is impulse, just like the area of the rectangles of the momentum square graphs in momentum. So, to repeat, the area of the rectangle on a V versus M is momentum, initial or final, and the area of any shape on F versus T is the amount of momentum gained or lost between the initial and final momentums. Some final takeaways. Only the first and fourth quadrants appear on our M and V square diagrams because velocity can be negative, but mass can't be. Only the first and fourth quadrants appear on our force versus time graphs because force can be positive or negative, but we can't travel backwards in time. Momentum square diagrams must be rectangular, and the area represents the initial or final momentum. An F versus T graph does not need to be rectangular, but it does have to be a function and pass the vertical line test. The area represents impulse, which is momentum gained or lost. That's it. Get to practicing.